Hi, we are going to choose the MOSFET for our buck converter, and we are going to see 3 rules for selecting the specific device we want. One comment, these rules are personal and they were set considering the specific scope of this project, so they are a simplification. So in other words, they are not general rules that everyone for other projects has to follow. Okay, so first rule, we are going to choose a MOSFET with a breakdown voltage that must be equal or higher than 1.5 the expected value. The expected value is the voltage we expect to see in our particular design. So basically we need to review what is the voltage across the MOSFET in a buck converter. This is something that we already studied in a previous video. So remember that we measured the voltage in this way, and we saw that during state number 1 the voltage across the MOSFET is 0, and then we have VI. So what is the expected value? The expected value is VI. So in our particular design, VI is 12 volts. If we multiply 12 volts with 1.5, we have 18 volts. So we are going to choose a MOSFET whose breakdown voltage must be equal or higher than 18 volts. Okay, this is the first rule. Second rule, the second rule is about the current through the switch, in particular about the average current through the switch. We measure the current in this way, and the second rule is the maximum continuous drain current must be equal or higher than 1.5 the expected value in our particular design. We already analyzed the current through the switch, through the MOSFET. The waveform is this one, and in that video we already talked about the average value of that waveform. It is duty cycle times output current. In our particular design, the duty cycle is 0.275 and the output current is 15.15 amps. So this is equal to 4.17 amps. Okay, so in this way we want a MOSFET whose maximum continuous drain current must be equal or higher than 6.26 amps. Rule number 3 is also about the current through the switch. Okay, this one. But now we don't talk about the average value requirement. We talk about the instantaneous value. So the maximum instantaneous drain current must be equal or higher than 1.5 the expected value in our circuit. So the current waveform obviously is the same. And now we focus on the peaks we see in the waveform. We already saw the expression of those current peaks. The expression is output current plus peak-to-peak current ripple through the inductor divided by 2. Here we have 15.15 amps, and here we have 3.03 amps. They are specifications of our design. If we replace the values, the result is 16.67 amps. If we multiply this with 1.5, we get our requirement is 25 amps. So we want a MOSFET that must be able to drive instantaneously at least 25 amps. Well, with this information we can check the different websites with components, with MOSFETs, and you will have a lot of options. I'm going to choose this one. This is the reference of my MOSFET, and the manufacturer is Texas Instruments, which is a very popular company. The breakdown voltage of this device is 30 volts, which is much higher than 18 volts. The maximum continuous drain current is 43 amps, much higher than, I think that was 6 amps. And the maximum instantaneous drain current of this device is 400 amps, which is much higher than 25 amps. And then we have two very important parameters of the MOSFET: the on resistance and the total gate charge. The first one has this value, and the second one has this value. The on resistance is the resistance of the MOSFET channel when the device is on. Okay, we don't have a perfect short circuit, we have a small resistance. So in this way, this on resistance allows us to estimate conduction losses. If we have a high resistance, we have high conduction losses. If we have a low resistance, we have low conduction losses. The second parameter, the total gate charge, is the amount of charge that we need to inject through the gate terminal in order to turn on the MOSFET. Okay, so in this way, this parameter doesn't allow us to directly estimate switching losses, but is good to see how the device operates in terms of switching condition. I mean, if you have a high total gate charge, you will have high switching losses. If you have a low total gate charge, you will have in general low switching losses, because you need to put less charge into the gate to source capacitance in order to turn on the device. So you need to put, let's say that you have a faster device. If you have lower total gate charge, you have a faster device that is able to turn on very quickly with less charge. Okay, and we have to take into account one important thing, and that thing is that in general, in the MOSFET, we have a trade-off between conduction and switching losses, because if we consider a MOSFET with low on resistance, in general, the total gate charge will be high, and if we choose a MOSFET with low gate resistance, with low total gate charge, the on resistance will be high. So there is a trade-off between on resistance and total gate charge, or in other words, there is a trade-off between conduction losses and switching losses. In any case, we are going to choose this specific MOSFET with these values. And finally, about the size, you can check the datasheet and make some numbers in order to see the size of the device. Well, one last comment. Let's see how we include the MOSFET model in LTspice, because this model is not included in the default version of the software. So what we are going to do is to put a MOSFET symbol, modify the name, and put the reference of our MOSFET, and then in the component configuration of the MOSFET, you have to ensure that here you see an X, another X here, and here. And here you must see the reference of the MOSFET. Then we need to download the library of this device from Texas Instruments website. Okay, so go to the website, download the file, is this one. Okay, and then you have to put this instruction in the LTspice simulation to indicate that you want to use that library. There are other ways for including a library, but this is the one that I have chosen. So put that instruction. In this way you say that you want to use that library. In the library is a file where you have a lot of information describing the operation of that MOSFET or the parameters of that MOSFET, and what you have to do is to put that library file in the same folder you have your LTspice simulation. Okay, so this is my file of this circuit, and in the same folder I put the library of that MOSFET. Okay. Well, one last comment. Since we change the ideal switch with a MOSFET, we need to modify a little bit the control of the switch, the control of the MOSFET. Okay. First of all, we are going to put a small resistor in series with the control between the, let's say, between the voltage control and the gate terminal is the gate resistor. We are going to use 10 ohms. It's a popular value, okay, something close to 10. And the second thing we need to modify is the pulse amplitude. Remember that our control signal is a pulse voltage waveform. In the case of the ideal switch, we work with a pulse voltage waveform between 0 and 5. Here we modify the pulse amplitude. We put 12 instead of 5 in order to properly turn on and off the MOSFET. So in this way, I think that we have everything about the MOSFET selection and how we include it in our LTspice simulation. So here we finish. In the next video, we are going to talk about another device for our design. So see you